After finding the critical moment acting on the slab, let us proceed with the following question. The question now asks us to design for the reinforcement using H10 steel bars. H10 steel bar means the high-yield steel bar with the diameter of 10 mm. The characteristic strength of this kind of steel bar is 500 Newton per mm square. From the previous questions, we obtained the moment equals to 9.56. Now you want to design for the reinforcement, taking the moment. You know that this loading of 9.56 appears at the support of the shorter span. Now if you are designing for the support of the shorter span, the reinforcement should be placed near to the top of the slab. To design reinforcement bar for the slab, you may refer to the floor chart here, which cover the singly reinforced and doubly reinforced concrete member. You know that the slab is probably the largest members for structural use in the structure. That means the panel is relatively large as compared to the load taken by it. It is more likely to be singly reinforced than doubly reinforced. Of course, we would like the member to be singly reinforced, as it is easier to design. At this moment, we cannot really tell what will be the outcome. Therefore, we will need to first determine decay using this equation. You have the moment equals to 9.56. FCK, concrete strength, equals to 30 Newton per mm square. The B refers to the width of the slab. For typical large member, we will take the width on basis of 1 meter width. That means the B here will be taken as 1000 mm. As for the D, it is the effective depth. The effective depth refers to the distance from the top of the slab to the centroid of the reinforcement. There are dx and dy, representing the effective depth in the shorter span and the longer span. For a typical slab, the more critical directions it will be at the shorter span. In order to take advantage of the effective depth in resisting the moment, we will use the larger effective depth in the shorter span. How do you do that? The reinforcement in the slab comes in two layers. One in the longitudinal directions, another one in the transverse directions. The more critical side, it will be placed at the bottom, while the less critical side, it will be placed on top of the longitudinal reinforcement. In another word, in these directions, it will be the shorter span. You will place this reinforcement at the bottom, and these directions, it will be on top of the other reinforcement. Now if you cut the sections here, view from the side, it should look something like this. The effective depth, it will be referring from the top of the slab to the center of the reinforcement. Now if the center is referring to the bottom reinforcement bar, the effective depth, it will be larger. Whereas if the effective depth is referring to the top reinforcement bar, the effective depth, it will be smaller. Since the slab is more critical at the shorter span, then you know that the larger the effective depth, it gives you greater resistance in the moment. Therefore, we use the D here as the dx. Calculating the x, you can solve it in the graphical manner. This is the height of the slab minus the cover and minus half of the bar size. In the questions, the thickness of the slab is 150. The concrete cover is 30. The bar size is 10. Half of the bar size, it would be 5 mm. You will take 150 minus 30 minus 10 divided by 2. That gives you 115 mm. Having all the value found, substitute into the equations, you get your K equals to 0.0289. Compared with 0.167, the K is less than 0.167. When the K is less than 0.167, you know that it is singly reinforced, as expectable from a typical slab. In the case that you get your K value greater than 0.167, based on my personal experience, it is not likely, especially when the thickness of the slab is relatively high, such as 150 or 125. Sometimes in the industry, you see the designer intend to reduce the weight of the slab by providing the thickness of the slab 115, which is the thickness equivalent to the thickness of the brick wall. As far as I am aware of, this is the thinnest slab that I have ever encountered, based on my personal experience. Theoretically, there is no restrictions for you to go thinner, but normally we do not see that in the construction industry. Now, if you use thin slab, this will lead to you very low effective depth. Having low effective depth, you may require more reinforcement bar to reinforce the slab. When the thickness is thin enough, it is still possible to have compression steel bars. But normally we would not do that. Why? Due to the cost of the material. You know that for a typical slab, you will need to provide reinforcement at the tension region in order to carry the moment. There shall also be reinforcement at the support, since there's going to be negative moment at the support. As for the compression part, you don't have to provide reinforcement at the compression part. Unlike reinforced concrete beam, even though you do not require compression steel bar, a typical reinforced concrete beam will have to have at least 2 H12, which is meant to tie the shelling for the beam, so that the shelling is in position. However, for the slab reinforcement, you do not require shelling, but you will have transverse reinforcement. In this case, it is not a must for you to provide the compression steel bars. Steel bar is more costly than concrete. 1 meter cube of concrete, based on the local supplier of my area, it costs only few hundreds. As a method to minimize the cost of the material, might as well you provide thicker slab with less reinforcement, where the reinforcements is just nice to meet the minimum AS. That should be the most optimum design. Therefore, by all means try to prevent the compression steel bar for a typical slab. Coming back to these questions. Now you get your K less than 0.167. No compression bar is required. Then you will adopt the K into the equations for the lever arm. Substitute 0.0289 into the equation. You get 0.974D. Your lever arm here should not be more than 0.95 D. As expectable for a typical slab, it is normally close to 0.95, and most of the case it will go beyond 0.95 D, which in this case it is greater than 0.95 D. You will use 0.95 D instead. Substitute the D, you get your lever arm Z equals to 109.3 mm. Then put the Z and the moment into the equations. Fyk is 500 Newton per mm square. The amount of reinforcement required, it will be 219 mm square. And then you may refer to the table of reinforcement for the slab. Given in the questions, you're going to adopt bar size of 10 mm. Look at the area of the reinforcement. Decide appropriate spacing where the amount of reinforcement provided is greater than the amount of reinforcement required. You can provide H10 300 that give you 262 mm square reinforcement area, since the table ends at the spacing of 300. Or actually you can try 350. The area of the reinforcement equals to 224 mm square, which is greater than 219 mm square. Now in the case that this table is not provided, you can still calculate it yourself. Now the question here is, how do you calculate it? First, you need to know the slab is designed on the basis of 1 meter width. Now when the size of the reinforcement bar is decided, which is 10 mm diameter, you can use the standard formula for circle to determine the area of one reinforcement, which is pi r square. The pi r square represents the area of reinforcement for one steel bar. Now if the reinforcement is spaced at 1 meter width, there will only be one reinforcement within that 1 meter width. Then the number of reinforcement, it would be 1 times whatever areas that you have calculated based on the pi r square. Now if you have 2 bars within that 1 meter width, that means the spacing of the reinforcement, it would be 500 each. When the spacing is 500, you will have 2 reinforcements within that 1 meter width. Then now your pi r square will be multiplied by 2. Same principles apply. Depending on the spacings that you would like to provide, divide the 1 meter width by the spacing provided. That gives you the numbers of reinforcement bar within that 1 meter width. And the number of reinforcement bar is to be multiplied with the area of 1 unit of reinforcement bar. That will give you as provided.